Hi, welcome back to this video, and I'm going to welcome myself back to this exact video again because I actually recorded the whole thing and realized that I didn't have my mic plugged in, which is super annoying. So I've actually written out the whole thing. So this has just been a really bad day of me messing up technology. It's the same day as when I recorded the previous video. It's just I'm going to put them out on different days. And you remember in the previous video there was there was like cursor mania where I had issues finding my cursor and then my computer crashed. So the misfortune continues. But what I'm going to do, because I'm a lazy bum, is I have already written everything out, so I'm not going to write everything out again. I'm just going to say everything again, okay? So obviously if I just like scrolled down, you could read everything, but you probably couldn't because my writing is really bad. So I'm going to say everything. We're going to prove in this video Chebotarëv's lemma, which combines all that we have learned in the previous three videos about cyclotomic polynomials and van der Waals determinants. Okay, so first I'm going to just go over what we know from the previous videos. So I hope you can see my cursor. You know what? It's going to be even better than that. I'm going to take a little thing and highlight stuff or underline stuff. Okay, so we've showed that the cyclotomic polynomial p to the cyclotomic polynomial, we defined that. I'm not going to define it again, but the if p is a prime, then the qth cyclotomic polynomial, where q equals p to the k, for some integer k, you evaluate that at 1, it's always going to be p, no matter which power of p that you choose for q. Then we also proved in the 2 videos ago that cyclotomic polynomials are irreducible, which means that they don't factor into products, so irreducible. They don't factor into a product of two integer coefficiented polynomials. All right, so that's what we know about cyclotomic polynomials. Okay, then we defined this called the van der Waals determinant, this polynomial, and it's given by this formula. So it's a product of all I less than j, zj minus zi. But then we also showed that it's given by this formula. So this expresses it as a sum over all pi in Sn, so permutations pi. It's the sine of pi times the product of zi pi, this is a, is pi I minus 1, okay? So these are monomials. So like right here, that's a monomial, and then there's n factorial monomials, all of this. Okay, then now we let n1 through nk be given, and we define a polynomial p that's, with indeterminate z1 through zk, and that's going to be the determinant of zi to the nj, of this matrix where each entry is zi to the nj. And I think we might have actually done zj to the ni, but it doesn't really matter because determinants are invariant under transpose. Yeah, I don't really remember. And that is also given by this formula, the same Leibniz formula, sum over all pi and sk, sine of pi, and the product of all these monomials, okay? Zi to the n pi I. So these two are actually the same. So the top is a special case of the bottom when n equals k and ni is equal to I minus 1 for all I, right? So here we have pi I minus 1, and here we have n pi I. So we want n pi I to be pi I minus 1. In other words, ni to be I minus 1. So that's why these are called generalized van der Waals determinants. Okay, and for any generalized van der Waals determinant, p, it's polynomial, it factors as p equals delta k q, where delta k is the non-generalized van der Waals determinant corresponding to k above, and q is some integer polynomial, such that when you evaluate it at 1, 1, 1, 1, 1, you get delta k of n1 through nk over delta k of 1 through k. Okay, so that's everything that we know so far. Now we're going to prove Chebotarëv's lemma. So before that, we're going to prove another lemma. I'm just really splitting the proof into two chunks for convenience. But this one is kind of encapsulating all the stuff we know about cyclotomic polynomials. The next one will have the van der Waals determinants. So it's convenient to just have some of these things in your brain at once and not everything. Okay, so this is going to tell us it's a criterion for when a polynomial is not going to vanish on qth roots of unity. Q's a prime power. Okay, so here's the lemma. I'm going to read it because it's everything's messy. So let p be a prime and let q be an integer power of p. So okay, that's little q. Big Q is going to be a polynomial, okay, with integer coefficients, z1 through zk. In k variables, the integer coefficients, and let q be such that q evaluated at 1, okay, is not divisible by p. Okay, then for any k tuple of omega 1 through omega k of qth roots of unity, okay, there has to be qth roots of unity, but it can be any qth roots of unity. Okay, we find that q doesn't vanish on these roots of unity. In other words, q of omega 1 through omega k is not equal to 0. Okay, so this is a statement that if something is not divisible by p, then some other polynomial is if q evaluated at 1s is not divisible by p, then q evaluated at any roots of unity is non-zero. We're going to go by prove the contrapositive though. So we proceed by contraposition. We're going to prove that if q is 0 on some roots of unity, then q evaluated at all 1s must be divisible by p. Okay, so that's what we're going to do. So we proceed by contraposition. Okay, so suppose that omega 1 up through omega k exists such that q of omega 1 through omega k is equal to 0. Okay, now let's let omega without any subscript, so just omega, be a primitive qth root of unity. And we know that any qth roots of unity are integer powers of one another. Like we've drawn the unit circle and everything, and reasoned that out. So since that's true, there are integers n1 through nk, here now. There are integers n1 through nk such that omega I equals omega to the ni for all 1 less than I less than k. Okay, so that's all good. Now we define a polynomial, another polynomial r, but this polynomial isn't an n variable polynomial, or a k variable polynomial, sorry. It's not a k variable polynomial, it just has one indeterminate. And it's given by, oh, I actually messed this up. So here we go. So r of z should be equal to q of zn1, zn2, all the way up to znk. Okay? Now, by the choice of omega before, r of omega is 0, because r of omega is just q of omega 1 all the way up to omega k. So since r of omega is 0 and omega is a primitive qth root of unity, r of z has to have a root in common with phi q of z, where phi q is the qth cyclotomic polynomial. So because they have a root in common, that means they have some non-trivial common divisor, right? But we know that phi q doesn't have any non-trivial common divisors, non-trivial divisors at all, right? It's irreducible. So that non-trivial common divisor has to be phi q itself. So, that's what I'm saying here. So since phi q is irreducible, okay, phi q of z has to divide r of z. It is that non-trivial factor, okay? So that means that r1 is divisible by phi q of 1. And r1 is just q evaluated at all 1s, and phi q of 1 is p. Okay, that's that thing that we did in our basic properties of cyclotomic polynomials a very long time ago, and it's the first thing that I said in what we know above. Okay? I hope that was okay. I realize I go a little faster because I don't have to write everything. So if you were trying to copy all this down, it's probably really annoying. But if you're just watching, then honestly, you might prefer this presentation format where you don't have to wait for me to write things. I don't know. It's a matter of taste. Okay. So now next is we're just going to prove Chebotarëv's lemma, which is really a theorem. Like, it's quite famous, and it's been proved many, many times since. people either didn't see Chebotarëv's paper or they prove it a different way. But Chebotarëv's paper came out in 1926. You know, it's kind of crazy that we're almost at the point where this is like ambiguous. But okay, anyway, 1926. And yeah, so let's just state it. So it's so let Q be a prime power. So it's, yeah, we don't even need the prime here, I think. Well, maybe it's P, maybe we're gonna use it later. Yeah, there you go. And I messed up. So let Q be a prime power. Q is equal to P to the K because we use P here. Okay? So let Q be a prime power. Let omega 1 up through omega K be distinct Qth roots of unity. Okay? And then let N1 through Nk be integers that are all distinct modulo P. P is that prime. Okay? So Q1 through omega 1 up through omega K are distinct, actual distinct numbers. N1 through Nk, they're going to be distinct modulo P. So they're actually not just distinct numbers. They actually have to be distinct modulo P as well. Then this K by K matrix, omega I, with the ijth entry being omega I to the nj, has non-zero determinant. Okay? And this is, of course, just that polynomial that we saw earlier evaluated at the omega i's, which is what I'm saying right here. So in the first line of the proof I say that. So let P of Z1 through Zk be this determinant, Zi to the nj, okay? And we can factor P, we know that, we can factor P as delta K times Q, and delta K is the Vandermonde determinant, times Q, where Q is some polynomial with integer coefficients, such that Q of all ones is equal to delta K, N1 through Nk, over delta K, 1 through K. Okay, that's literally up here. It's in what we know. Okay, that was in the previous video. All right. So that's this. I'm just gonna I feel weird not writing anything while I talk, so I'm gonna draw little boxes. Okay, so we want to show that P of omega 1 up through omega K is non-zero. So to show that it has non-zero determinant with all these powers with all these roots of unity in there. Okay, so delta K of omega 1 through omega K is already non-zero because omega 1 up through omega K are assumed to be distinct, and in this this Vandermonde determinant is a product of their differences, right? It's omega j minus omega I for all I less than j. So they're all distinct, which means that product is non-zero. And so it's enough to show that Q of omega 1 up through omega K is non-zero. Okay, but now we're in exactly the domain of our previous lemma. So this lemma was finding a non-vanishing criterion, right? So we want to show that this doesn't vanish on roots of unity. So by the previous lemma, this reduces to showing that Q of all ones is not divisible by P. Okay? So what we know what Q of all ones is, it's this fraction. Okay? And in fact, in the previous video, we showed that delta K of 1 through K is actually 0 factorial, 1 factorial, all the way up to K minus 1 factorial. And, I guess we are going to need that there's no P here. I think in the notes came, so we do want K to be less than P. Let's just be safe, and we're going to say K is less than P. Okay? I think it's actually in the statement. I just forgot it. In the book, I think it's in the statement. Okay. Whatever. There's no P appearing in the denominator. That's not really that important even. It's really the numerator here, right? So the numerator, we want all these to be not divisible by P. Okay, but the numerator is exactly this product here of this nj minus ni for all I less than j. And we didn't just assume these numbers and I to be distinct, we also assume them to be different modulo P, which means modulo P, all of these differences are non-zero, and you multiply a bunch of things that are non-zero in a an integral domain. I mean, actually, ZP is a field. You multiply all these things, you're going to get something that's non-zero. So this is non-zero modulo P, and that's the end of that proof. So Chebotarëv's lemma was really, really simple. Once we we sort of took all the annoying things about this proof and we put them in the previous video. So now we have something very simple, but we've shown that, you know, for any integers that are distinct modulo p, any distinct qth roots of unity, this matrix here, which is a generalized van der Waals determinant, is non-zero. Okay, and in the next video we are going to prove state and prove Tau's uncertainty principle for ZP. We've actually already stated it. We you know, very long time ago we showed that well, it's exactly this, right? It's so if f is some function from ZP to C, we want to show that the support of f hat plus the support of f is greater than or equal to p plus 1. We want to show that, and all we're going to need is Chebotarëv's lemmas, which means you can kind of forget all the things that we've learned. Okay, you can't forget everything, but like you don't need to remember all those preliminary statements. You just need to remember Chebotarëv's lemma and all the definitions. And we're going to be able to prove this stronger uncertainty principle. Remember, the general uncertainty principle was that if you times these two things, you get something that's greater than or equal to p, right? But that works this way. This works for any group, not just p group, not just said p. Any group, it's going to be the size of the group. Okay, the size of the group. But when z equals zp, you get this one. Okay, and it's a lot stronger. Anyway, I already talked about that in a previous video. I don't know why I'm saying it again. Yeah, so that's what we're going to do next video. It's probably going to be a little bit longer because I want to put it all into one place, the proof of Tau's uncertainty principle. But that is what we're going to do next time. And until then, I will, yeah, go off and enjoy your life.